Okay, let's review what we left last time, and I want to make sure that the spelling of this person is right. So we talked about Dutch's algorithm. So it's one of the quantum algorithm. Well, I can't say this is the earliest, but one of the earliest quantum algorithm. And before I start, let me clarify what quantum algorithm means. So quantum algorithm is a quantum circuit that solves a computational problem. So whenever you talk about quantum algorithm, you need to talk about what is the problem and how do we design a circuit. So what is quantum circuit? Let me clarify that one again. So computational problem is basically clear. So it's whatever problem you want to understand, whether it can be solvable in the classical computer or not. As long as it deals with the bits 0 and 1, you can implement it into quantum algorithm. But anyway, quantum circuit is a series of quantum gates. So not always, so if you're dealing with the quantum gates on 1 qubit state, that's not fun. So it's usually on n qubit state. Which applies sequentially. So I showed you the diagram that shows the quantum circuit last time, and you go from left to right, and it's the time axis, and you want to apply that kind of quantum gates on your qubits. So I'll just put the quantum circuit of the Dutch's algorithm directly, and then let's review our computation one by one. So first, there are two qubits. And in quantum circuit, we call it register. So register equals to quantum qubits represented by a horizontal line. So it's first initialized at cat0 state and cat1 state. It's easy to initialize a quantum state because if you're dealing with electron spin, then you can apply the magnetic fields in one direction, and then the electric spin aligns in certain direction. So it's fairly always, so initialization operator, in some sense, initialization operator always comes with the implementation of qubits in the quantum computer. So the first quantum gate that you apply on both of these registers is the Hadamard gate. And then you apply the oracle. So we talked about the oracle. So the upper one is the input register and the bottom one is the output register. And then you apply the Hadamard again and take the measurement. So here, let me write again. So what this oracle is. So whatever your state is, let's say this is the base state, and this is also base states on input register and output register. The oracle changes the output register only. It doesn't do anything on the input register. So in this Dutch's algorithm, what it does is that it's in the Dutch's problem. There is a Dutch's problem. We talked about it last time. And it is about function from 1 bit and to 1 bit. And the output register is turned into this way. So knowing this, go back to our DGIST algorithm, you can see something is weird in an intuitive sense. So the oracle doesn't do anything on the input register. X goes to X, nothing, right? So we apply the Hadamard gate on the input register and pass through the quantum oracle. Didn't do anything, which doesn't do anything, and then apply the Hadamard gate again, right? So it's something like you apply Hadamard gate twice. So remember what Hadamard gate is. So it's just 1 qubit gate, and you can represent it as 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. Well, if you take the square, what is it? Just identity gate, right? So you can kind of guess that what's the, I mean, you can imagine what is going on here. We don't do anything. I mean, we just revert our original state at here and then take a measurement. So you can imagine that your output or observation will always turn out to be 0. But it doesn't. But it's not. It's not how it works. So there's a famous saying that have anyone heard about this saying? I think I mentioned last time again. So whenever you are dealing with the quantum computing, also quantum mechanics, you have to check your computation. Don't rely on your intuition. So it's said by David Mermin. I didn't know. I heard about this quotation, but I didn't know who said it. And I Googled it, and then it turns out that it was the author of this book, which I'm using almost as a textbook. I think I mentioned it as a textbook too in the syllabus. So it's the author of this book. I think there is a book in the library. If you have a chance, you can read this. And yeah, so don't think what will happen without computation whenever you see a quantum circuit. So let's try to compute. So when you compute it, just do it one by one. So I'm going to split the stage into 4. So here is the initialization stage, which is indexed as 0, and first stage, second stage, and third stage. So at the third stage, all we have left is the measurement on the input register. So let's do it one by one. So here, we're gonna put it C for the measurement. And okay, so I'm going to, so let's see. Question? No? So I'm going to write the psi I to be the, so this is 2 qubit state. At the ith stage. Okay. So let's see what happens at the psi 0. So we initialize it to 0, tensor 1. So I just indexed arbitrarily that the bottom one is the index 0 qubit and the upper one is index 1 qubit. It doesn't matter as long as you keep which one is input and which one is output. So, and then let's compute psi 1. So basically this is exactly the same what I did last time, but I did it really fast. So I want you to follow through one by one, because it's going to be get more complicated as we progress as we dealing with another quantum algorithm. So anyway, so 0 becomes plus state and 1 becomes minus state. And plus state is 1 over square root of 2, 0 plus 1, and tensor. And minus state is 0 minus 1. And the coefficient in the tensor product can move freely wherever they want. You can even put it outside of the tensor product. So let's put it that way. So 1 over 2. And then the tensor product between 2, 1 is written as the abbreviation notation. So we have 0 cat tensor product as 0, 0, right? and 1, 0 as 1, 0, and now it's minus 0, 1, 1, 1. Right? So that's our psi 2. So it's a superposed state, but still it's entangled. It's not entangled state, right? So you can split it into one tensor product. So let's talk about psi 2. What happens? Now we are passing through the oracle. So it looks up what's the base state of the input register is and then do something on the output register. It doesn't do anything on the input register. So 1/2, 0, F0. So see, 0 plus F0 is the formula, but it's the same thing as F0. So we are taking a binary addition, remember? And it's 0, F1, okay? And then we have 0 and 1 plus F0, but when you add 1 to any binary digit, it flips. It goes to opposite. So F0 bar. So bar means the opposite of F0. So if F0 is 0, then F0 bar is 1. Okay? That's what I mean. So, and then 1 F1 bar. Again, because we have 1 plus F1. Now, we can simplify from here, but let's do one more step. Let's compute psi 3. So psi 3 is now 0 becomes plus and 1 becomes minus. So I'm going to write everything completely clear. So plus F0 and minus F1 and plus F0 bar and minus F1 bar, right? So and then let's write the plus and minus as a superposition of ket 1 and ket 0. So then you have 1/√2 coefficient everywhere. So I'm going to combine it to here. So it's 1/2 so that I don't have to worry about the coefficient anymore. Just think about 0 and 1s. So we have 0 ket and 1 ket with the positive signs. So 0, F0 plus 1, F0, right? So these two come from this one qubit state. And this one, we have 0, F1 minus 1, F1, right? Because I have minus, which has minus 1 ket. And here I have minus 0, F0 bar minus 1, F0 bar and minus 0, F1 bar plus 1, F1 bar. So that's the final stage. And let's simplify a little bit more. So I'm going to collect all the base states. So these are all base states, see? So there are many, so there are 8 summands. So it means there should be some overlapping. So there should be some terms that are actually equal each other. But we don't know what the value of F0 and F1 is, so we're gonna just leave it as 8 terms. But all we can do is just combine it with the same ket state on the input register. So look at the zeros here first. So it's 2 √2, 0, tensor product. Now let's put the center product back here and then read everything on the output register. So here F0 and plus, no, this is not 1, this is 1. So we have to go here, right? F1 here, and then here is minus F0 bar, and here we have minus F1 bar, Okay, that's all I have for zeros on the input register, and plus 1 over 2 square root of 2, 1, and then collect all the states where it has a 1 in the input register. F0, and here minus F1, and here minus F0, and plus F1. Okay. All right, so what's next? Now, we apply the Hadamard, we apply the algorithm, quantum circuit, assuming that there is a quantum oracle based on a given function, and we don't know what the function is. So here, we cannot conclude anything, but let's assume that we have certain situations. So for example, let's assume that we have f0 equals to 0, f1 equals to 0. So this is the case of constant function. So remember that the goal of this Dutch algorithm is to determine whether function is constant or balanced. So this is an example of constant case, and see what happens for psi 3. So if function has these values, what would be the psi 3? Just plug in their numbers, plug in zeros and zeros here. So this is 0 cat, 0 cat, and this is 1 cat, 1 cat, right? Everything is 0, but we have opposite, so 1, 1. Now how about here? 0 cat minus 0 cat, minus 1 cat, plus 1 cat. So 0 cat, 0 cat cancels out, minus 1 cat, plus 1 cat cancels out. So we don't have this part. So only this part, but what's the coefficient of each base state? We have 2 of each cat 1 and cat 0. So we have 2 cancels out, so we have 1 over square root of 2, 0, tensor product, 0 minus 1, right? So this is the input register, and this is the output register. Okay, that makes sense. Well, it's not contradicting our intuition, because we thought that this is not going to happen. This is just going to be the same 0 cat whenever we take the measurement, because we just applied Hadamard twice. But let's see what happens when we had a function value which is balanced. So so it's just an example. There are total 4 cases, but I'm going to show you just 2. So f1 equals to 1. So this is balanced case. So let's plug in here psi 3. So again, so 0, 1, okay? Cat 0 plus cat 1 minus cat 1 minus cat 0. So there are cat 0, cat 1 with a positive sign, and cat 1, cat 0 with the negative sign. So they all cancel out. So there's nothing in the first summand here. But how about the second one? So this is cat 0 minus cat 1 minus cat 1. So there's 2 minus cat 1. So 2 cat 1. And plus cat 0. So there are 2 cat 0. So you cancel out 2 here. So we have 1 over square root of 2, 1, tensor product, 0 minus 1. Okay. So again, this is input state, and this is output. So it doesn't matter what output is. I just want to take an input measurement, input register. So if I had this situation, if my function were this, then all I can see after taking measurement on input register is just 1, right? And you can imagine that it happens only when, not because the specific value of the function, it's because of the balanced state or constant state of a function. So you can see why is it true by looking at this. So it's weird, right? So at first, it seems like it doesn't change the state because we're just doing nothing here. but it actually changes the state. And it's not the output that we take a measurement. We take the measurement on input to find out information about the function. Do you have a question?
I think it shows the same result in case of f0 equals 1.
F0 equals 1 and F1 equals to 0? You mean the balanced case?
It may be the same as case 2.
Yeah, so you get the same, you get the negative sign, I think, somewhere here, when you have F0 equals to 1, F1 equals to 0. So it doesn't matter what the output state is. Input register has to cat 1.
F0 is 1.
Yes.
F1 is 1.
Yes, so if you have F0 equals to 1, F1 equals to 1, you still get 0 cat on the input register. So I think the output register will change its sign. Yes, but it doesn't matter. We're not going to take a measurement here. It's not really important. What do you mean? Because our goal is find out what type of function that the oracle, that defines the oracle. So it's only determined by the input state. Right? So that's why Mermin said, shut up and calculate. Don't just stare at the circuit to find out what the information you can get. You're not going to get any information intuitively. So every quantum circuit or quantum algorithm you are going to see is similar to this type. So you have to be familiar with this. So if you have any question, let me know right now. No? It's comfortable? Okay. So let's talk about Dutch-Sosa algorithm. As you can see, the name indicates that this is a little bit of generalization of Dutch algorithm. So Dutch-Sosa algorithm. So again, quantum algorithm consists of quantum circuit and the problem. What's the problem? So the problem is, the computational problem is, classify the given function into one of two. One is constant, the other is balanced. Find whether the function, so this function is not as simple as Dutch's algorithm. So in this case, it's a function that sends n-bit string to 1 bit. N-bit number, you can say also n-bit number to 1-bit number. Okay, so n-bit means that you have 2 to the nth power of numbers in your domain, and always the value of function is either 0 or 1. So the notation that you have of n, I have n on top of this set symbol, is that it's just you can consider as a product of n same sets, 0 and 1. So when you take the n-bit number, it's just a matter of which number between 0 and 1 you choose for each digit, right? So that's what it means. Function is balance or constant. So that means whatever the value, whatever the input is, so x now is not 0 and 1. It's n-bit digits or n-bit number or n-bit string. So I'm going to put just x here again, is 0 or 1 for all x, or balanced. I.e., so the number of the x inside of domain whose function value is 0 is equals to the number of points in your domain whose function value equals to 1 is the same. So let me say it again. So this is the number of x in the domain such that f of x equals to 0, and same for here. So you take the, I write the absolute value sign to indicate it's the size of the set. So the f inverse 0, well, if you want to be that, I mean, this is a common notation in mathematics to indicate it's the preimage of the function, which means that it's a collection of all the input values whose output is 0. It's not saying that f has an inverse function. Okay, so don't confuse with inverse function. It's not a notation of inverse function. It just means that it's the preimage, the set, the subset of a domain whose value of function is right here, 0. And same for here. And the absolute value sign means the size, the number of elements of the set. Now, here's the important assumption here. What if the function is neither constant nor balanced? Because we are dealing with n bigger than 1, right? So if n equals to 1, it goes right to the Dutchess problem. So we assume that n is bigger than 1. Then not all function is either constant or balanced, right? So we have assumption that in this problem, important assumption, that the given function is always, we don't know what that is, but we know that it's always either constant or balanced. Okay? So that rules out many possibilities, but still, how can we find that? So think about classical algorithm. Think about classical computer finding whether the given function is constant or balanced. How many times do you have to ask that function for the value? So in the classical case, or classical solution, if you're lucky, let's say you tried 0 in your input, like 0, 0, 0, n times 0, and you got f of 0 equals to 0, okay? And then you tried 1. 1 means that it's 0, 0, 0, and then last digit is 1. And then you got f of 1 equals to 1. So you got two different values. Then because of this assumption, oh, this function must be balanced. Because if it's not, then it has to have the same constant value for every input, but we got the different value. That means it cannot be constant. So we know that it's balanced. So if you're really lucky, you can get the information whether it's constant or balanced in two queries, by asking twice what the value of function is. But what's the worst case scenario? How many times do you have to ask functions? Yes, that's the worst case scenario. Like, I mean, that's have a low chance, but you accidentally pick up all the inputs that has the same value. You want to stop there, but it could be the next value you ask is another value that you didn't find out for the rest of this 2 to the n minus 1, right? So you need at most 2 to the n minus 1 or plus 1 queries to find the solution. All right? So now, what is the Dutch-Stoss algorithm? So quantum solution you can find it by one query. That's quite surprising, right? So in the classical situation, you have exponentially many times to add to, the queries to find out the solution. But in the quantum state, it's just one query, right? So 1 is still a small number, but the important thing is it doesn't grow. The number of queries to find out the solution doesn't grow as the size of the problem increases. So if n goes larger and larger, your domain, the size of your domain gets larger exponentially. So usually the classical problem like NP-hard problem is like this. So size of a problem increases, then the number of computational complexity grows exponentially. But most of quantum algorithms, which are known to be effective, are something like this. It doesn't depend on the size, or it grows really slow. So now let's see what happens. Let's see the actual circuits here. So what we have here is input and output, right? So input state has n bits, right? So we need to prepare n qubits for input register. So I put the n here. So when I put 0, it means that there are n zeros, right? So remember what I introduced in the, I think, 3rd and 4th class. So we can write 0, 0, 0 n times, but you can also think of this as a bitwise or binary representation of integers. So when I say 0, it's just integer 0. And if I write that as an n-bit binary representation, it becomes the base state of n-qubit state. So that's the input and that's output. So output is initialized at 1 qubit. Okay? It's just single qubit. And then apply Hadamard. Oh, by the way, so although I'm recording this lecture, I made several videos about the quantum circuit or some quantum algorithm and a bit more, and uploaded on the YouTube. I made it on last semester, so you guys probably know where my YouTube channel is because I linked it in the LMS site. So if you go to my channel, then you can find somewhere in the 2nd or 3rd of my YouTube channel homepage that I have a playlist of these quantum videos that explains about these quantum circuits. It's a very short video, and I go really a little bit fast. So, but if you want to review it or learn about it before we learn it in the class, you can watch it. So anyway, so that's the first quantum operator. And then you apply the quantum oracle. And then also, by the way, so when you apply the Hadamard gate, it's not one Hadamard gate. Actually, you apply Hadamard gate on every single input qubits. Okay, so we have n Hadamard gates, and each of Hadamard gates are product by tensor product. So I'm going to rewrite it as this. So this is also common notation that you put the a superscript O times an n here, which means that it's the n qubit gate whose gate on each qubit is Hadamard. And then apply Hadamard and do nothing here and take a measurement. So when you take a measurement in this case, so you have to take a measurement on every single input register. So you have n qubits, so you take a measurement on every n qubits. So we do the same thing as before. Let's compute the quantum state on every stage. So this is 0, 1, 2, 3. Okay. So by the way, the quantum oracle is the same thing, almost same thing. So you have input state. It's an n-qubit state, so I put n in the subscript, and output state here. Then the quantum oracle doesn't do anything on the input state, but it changes the output state as follows. So f of x, the value of function is either 0 or 1. That's our definition of the Dutch-Stoss algorithm. Okay, so this is just 1 bit O plus 1 bit. Okay, so always 1 bit. So it's 1 qubit state. So what is psi 0 first? Let's just 0, 1. And let's apply Hadamard gate. So 1 ket becomes minus ket. But how about this n qubit state? So again, let me rewrite again. So we have n zeros, n qubits with initialized at ket 0. So we have H0 tensor product H0. So that's what really happens. So if I can put one more line here. So what happens is H tensor product H. So there are n number of Hadamard gate tensor product each other. So this becomes n qubit gate, and it's applied to 0 tensor 0. This is also n. And then we have minus state. Okay? So that's what it means. Okay? So when you have this kind of operator, then what happens is you apply that operator on the same index to the qubit of the same index. So we have H0 tensor product H0 and square root of 2, 0 minus 1. And there are all plus ones, plus kets. So we have plus tensor product plus. So I'm going to keep the output state as this forever because I'm not going to mix it. So look at this plus ket, tensor products of plus kets. What does it look like? It's always superposition of 0 ket and 1 ket with the positive signs. Let's take out the coefficient first. So each has 1 over square root 2. How many are there? So there are n. So I can take out 2 to the n over 2 outside. And everything is 0 plus 1, tensor product, 0 plus 1, tensor product, and 0 plus 1, and 1 over square root of 2, 0 minus 1, right? So don't do anything here. What happens if I combine this? What happens if I distribute all the tensor product each other to make it one n-bit string or superposition of n-bit base strings, base kets? So it's just a matter of which ket I choose for each of index. So if I choose 0, 0 all the way up to here, I get 0, the integer 0. So if I get 0, 0 for the first n minus 1 qubit and take 1 on the end, then I get integer 1 as a binary digit, right? So we have 0, 1. So these are n qubit state, and up to what? If I choose 1 for every qubit, then I get 2 to the n minus 1. Right? So how many are there? There are 2 to the n ket state. They are superposed with the same coefficient. And then let's write it as this way. Okay. It makes sense? Now, what do we do? That's the second stage. What do we, first stage, right? Yeah, still going on the first stage. So what do we do on the second stage? We apply the oracle. So let's compute psi 2. So here, 2 to the n over 2. So you can throw in, so you can consider this as these times the tensor product with this, but you can also think this as 1 over n over 2, the summation from x0 to the n minus 1, and x n tensor product 1 over 2, 0 minus 1, right? Because tensor product is linear, bilinear. So you can always split as if it's just the same way we can split our linear combination into some linear combination of each summons here. So we have in this expression we have one tensor product. In this expression we have superposition of n or 2 to the n minus 2 to the n tensor products, right? So let's think of this way. So what happens is we apply the oracle, which is a quantum gate. So every quantum gate is a linear combination, a linear transformation. So we can apply to each of these terms in the linear combination. So we apply UF on each of these terms. So it's going to be x from 0 to 2 to the n minus 1. The quantum oracle applied on xn and 1 over square root of 2, 0 minus 1, like this, right? So this is equals to same summation. So we don't do anything on the input register, it's just the same xn. But how about on the output register? So 0 becomes 0 plus f of x, so it's just f of x. And it's just one bit string, one bit number, so we don't put the subscript here. And then f of x bar. Okay. If you work this way, there's no problem, but it gets complicated. So let's introduce a clever way to see it. So whatever your f of x is, either 0 or 1, it's going to be plus 0 minus plus ket 0 minus ket 1, or plus ket 1 minus ket 0, right? There are two cases. So here, let me write here. So if f of x, so for each case, for each x, I'm doing for each x, if f of x is 0, then this part is 0 minus 1, right? So how about this is 1? F of x equals to 1. Then this becomes 1 minus 0. So what's the difference? The only difference is the sign, right? So f of x equals to 0, you get kind of minus, kind of, see? I mean, so you need 1 over square root of 2. Yeah, so it's not right. But anyway, so 0 minus 1, but when you have 1, you get the minus of this. So how can you rewrite this part? So you can rewrite this as square root 2, square root of 2, and then put the symbol here, minus 1 to the power of f of x, 0 minus 1. Okay? Make sense? Okay? Sorry. All right, so that's the second stage. Let's compute the third stage. So what do? We apply Hadamard gate on every n input register. So every cat x, we apply Hadamard. Okay. So 2 to the n over 2. So Hadamard gate are applied into whole quantum state, but so we only apply to input register. But again, Hadamard gate is a linear transformation because it's a quantum gate, so we can always put that into the summation. So we can apply Hadamard gate on each of this proposed state. So what is this? So let's compute this. So we don't know what x is. Well, I don't know what x is, but let's say if my x has a representation xn minus 1, xn minus 2, up to x1 and x0 in the binary representation. Well, for example, if I have 0, then it's 0, 0, 0, 0 all the way up to the end. And if it's 1, it's 0, 0, 0, 1. And if it's 2, then it's 0, 0, 0, 1, 0. Well, that's what I'm saying here. So, and 2 to the n minus 1 is just 1 all the way up to 1 here. So let's say whatever my integer is, let's denote each bit on digits as xi. So xi is either 1 or 0, and this is the digits, binary digit or bits at the i's place. So let's see what happens when I apply Hadamard gate on that. So this is h on xn minus 1, which is one qubit state. Okay, so x cat is split into the tensor product of cat and cats, where each cat has this base state, 0 or 1. And then Hadamard xn minus 2 and Hadamard x0. So and then how do you represent this? So if xi is equals to 0, then hxi is what? 1 over square root of 0 plus 1, right? So and then, I mean, since there is only two cases, if xi is 1, what happens? This is equals to 1 over square root of 2, 0, minus 1. The only difference is the sign of the cat 1 state. It becomes plus to minus. So we can write each of these states as following. So 1 over 2, 0, plus minus 1 to the n minus 1, 1. So the first one, let's say, if xn minus 1 is 0, then we get a plus cat. That's how I get this plus cat here, because minus 1 to the power of 0 is 1. When xn minus 1 is 1, then I get the minus 1 to the power of 1, so I get the negative cat 1, right? And then all the way up to the last one, which has 1 over square root of 2, 0, plus minus 1, x0, 1. Okay? It's confusing, so let me erase this part. Okay. So how can I write this? So this one becomes 1 over n over 2. So again, when I apply Hadamard, then I have n of 1 over square root of 2. So I get another n multiple of 2 to the 1 over square root of 2. So I can take out outside. And this is still here. So x summation on x is still here. And what I do have is tensor product of that kind of state. So let me write the big tensor product here, just to abbreviate all these dot there. So I is from 0 to n minus 1, and then 0 plus minus 1 xi 1, right? That's the state input register, and the output register is the same. Minus 1 f of x square root 0 minus 1. Okay? Well, it's still complicated, so I want to write it as, okay, so let's simplify it as far as we can. So I can simplify this as a 1 over 2 to the power of n, okay, and x from 0 to 2 to the n minus 1, but that's not changing. So how about this part? So how about that part? How can you simplify it? So basically, look at this part again. What you will get is just, whatever you get is just the choice you make at each tensor product. You have to make a choice whether you pick 0 or 1, right, on each digits, right, each places. But depending on how many times you choose 1, your sign of your ket state, which is the base state, is going to be changed. It's not going to be always positive like this one. So in this case, we always had a plus on the ket 1, so always get a plus sign. But since there is a minus sign, depending on the digits, so you're not going to get always plus or always minus. So how do you determine the sign then? So I know that it's going to be another big summation from 0 to 2 to the n minus 1. If you choose 0 and 1 on each places, you're going to get some number in between 0 and 2 to the n minus 1. But what's going to be the sign? How do you determine the sign? So here you have some. Can you think about any formula that determines the sign?
I'm just picking one. I'm just picking one.
Yeah, so let's leave it as a blank here. So let me just finish up the other computation. So what's next? So do you understand this format here? From here, from here to here. So the last part is minus 1 to the f of x of 1 over square root of 2, 0 minus 1. Okay? So you understand that how we move from this format and formula to this formula. Okay, it should be of this kind. So my question is, how do you write the formula of your sign? What do you think? So let me give an example. Let's think about examples. Okay, so let's say my x. So there are two index runs from 0 to 2 and to the n minus 1. So first x came from the first Hadamard gate applied here. And the second index y come from the second Hadamard gate applied on the input register. So let's say our n equals to 3, x is 1, 0, 1, and y is 1, 1, 0. Okay? So what's going to be the sign of this cat y? So let's compute this. So this y is chosen because, so first of all, if I write according to this x, then my sum end, this hx is going to be h3x is going to be 1 over square root of 2, 3, and then it doesn't matter, it doesn't really important here. So 0 minus 1, tensor product, 0 plus 1, yes, 0 minus 1. And this y is chosen because I chose this, 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 right? What's the sign then? Minus. So it's not always the choice of how many times I choose 1, right? It's when I choose 1 in the place of that digits of y, then and at the same place, my digits of x is also 1, right? So I need to count, kind of, yes. So I need to count whenever I have the same 1 on the digits here, right? So how can I express that? So I think you guys, some of you guys are computer major. So what kind of a logical operator does that? So yes, X gate, AND gate, yes, AND gate, yes, kind of AND gate, right? So if you think of 1 as a true, not false, 1 as true, then you get an AND gate, right? So whenever you have both true, everything will be true. So this thing is something like x0. Let me write it bigger. So x0, y0, all the way up to xn minus 1, yn minus 1. Does it make sense? So when you do this, then everything except when xi and yr are both 0 will vanish because one of them should be 0. So you leave out all the cases when xi and yr are both 0, and then you add them together, which means you want to see the parity. So if there are odd number of cases, then you get odd number of minus ones multiplied, so you get the minus sign. So you get, if you have an odd number, you get minus 1 to the odd is minus 1. And if you have an even case, you choose even number of those minus 1, so you get a plus 1. So that makes sense, right? So this is an important notation, so I'm going to introduce another symbol to represent this formula. So again, so this x and y is not, it's a number, but you can also think about this as a binary digit representation, which is almost like a vector because it consists of n binary numbers. So I write that formula as x times y, but it's not really times, it's more like an inner product. Okay? So x inner product y, if you think of this x and y as a vector, has the same formula, right? All right. Now you see why I started with the saying, shut up and calculate, right? So you need to calculate, see what happens. So that was the third stage, right? That's the third stage. I hope so. Where did I start? Oh, so this is the third stage. Yeah. So now we're done. Basically, what we left is the measurement. But if you leave like this, then it's kind of it's a bit confusing. So let me simplify a little bit more here. So 1 over 2 to the n x and y, and then minus 1 f of x plus x times y of y n, okay? And then now it really doesn't matter what the last part is. So I'm gonna put the 1 over square root of 2 ket 0 minus ket 1 as minus ket here, okay? And then I'm gonna switch the order of the summation. Okay, so let's see what happens. So 1 over 2 to the n, let's put the y first. Okay. And then we'll just write everything again. So f of x plus y. Okay. So then if I switch the order, what happens is all things here becomes just the coefficient of ket y. You see, at the end, I only get the ket y. I only use the information of x to determine the constants of this ket y, the coefficient of ket y. So if I reverse the order of summation, then this summation on x is always just what happens to do with this coefficient of ket y. So let's now have a simulation. So if the function, so maybe I'll give an example after we simulate. So if f of x, or just f, is constant, then what happens? So assuming that f of x is constant, which means, for example, assume f of x equals to 0 for all x, what happens? This psi 3, so this one is always 0, so it's 1 over 2 to the n y and x minus 1 x times y and y times minus 1. Can you simplify it further? What happens to all this coefficient? So again, here, let me give an example for y. So when y, so let's say I have a special case when n equals to 3. Let's say y is 0, 0, 0. And let's consider a bit, some few cases. Let's say 1, 0, 1. There should be up to 1, 1, 1. Okay. So what happens when y is 0, 0, 0? What's the constant here? What's the coefficient?
0.
Really? Because everything is 0 as in the exponent, which means that this minus 1 to the power is always 1. How many times do you add 1 here? So I omit the index here, upper and lower, but x and y, in this case, since n equals to 3, are run from 0 to 7. So there are 8 summands in each sum. So there are 8 ones added together here, right here. Okay? So when y equals to 0, so I'm splitting all the cases when y is running from 0 to 7. So when y is 0 in this sum, it becomes 8 times 0, right? How about 0, 0, 1? What's the coefficient? So now, well, you have to work with this big sum, 0 to 7 of minus 1x times 0, 0, 1, right? Now, think carefully. So let me write this way. So here, the binary digits. So think carefully. So if you do that, then you are taking x0, x1, x2 as a digits of each place, and x2 times 0, x1 times 0, x0 times 1, right? What's the result? And then you see, it's okay. I mean, minus 1 is what?
If x is odd number.
When x is odd number. Yes, basically, yes, that's right. So when x is odd, then you get a minus 1. When x is even, you get a we get a plus 1, right? So let me see this way. So you have x and x2 times 0, x1 times 0, x1 times x0 times 1, right? So basically, sorry, I don't have space for here. It's saying that I'm multiplying, I'm having 3 terms multiplied together for index from 0 to 2 of the summation of xi from 0 to 1 of minus 1 xi. Sorry, so not xi. So here, oh, that's right. Yes, sorry. So xi. Yeah, so xi here. Does that make sense? Sorry, so for to just put yi here. So yi, so y2 is 0, y1 is 0, and y0 is 1. So I should have put this in at the end, but let's have one more step here before I give you the final formula. So here, what is this saying is about is, let's look at the x2. So when I run my x from 0 to 7, I'm just choosing x0, x1, x2 in between 0 and 1, right? So let's think about x2 cases only. So x2 is changing from 0 and 1, but when x2 is 0, it's going to be 1, right? So let me write this way. So when x2 is 0, it's going to be 1, and x2 is 1, then it's also 0 because I multiply with 0, so it's going to be also 1, right? So that's the case of x2 equals to 0 or 1. And I multiply it to another minus 1 to the power of something. So let me write this way. So it's minus 1 to the power of 0 plus minus 1 to the power of, so this one is 0 times 0, and this one is 1 times 0. So I'm just splitting the case x2 equals to 0 and 1. So that's where this comes from. And how about the second one? So this is when x1 is either 0 or 1. So minus 1 to the power of 0 plus times 0 plus minus 1 times 1 times 0. So 0 is just constant here. And the last case, so these are 2, 2 and 2, right? It's not 0. But look at the last one. What happens? So that's when I change my x0 either 0 or 1. So when x0 is 0, I get 0 times 1. But when x0 is 1, that I get 1 times 1 as an exponent. So here I get 0. So I get this 8 summand, 8 terms by expanding this multiplication. And if you look at this way, then it's obvious that you always get 0, right? Because we are multiplying 0 with non-zero terms, right? So now you don't have to do for any other cases. You can generalize simply from here. So look at that. Look at that thing here, right here. So this x minus 1, x times y is nothing but product. So this is a product. How many times? N times. For each index, 0 to n minus 1, of sum of each xi, either or 0 or 1, just 2 summand here. And what we are adding each other, you're adding minus 1 to the power xi times yi, right? That's what we are doing. Okay? So, what is that? So, if you have any one of index I such that yi is not 0, which means yi is equals to 0, then in that place, you will get sum of minus 1 to the power of 0 plus minus 1 to the power of 1, which means you're adding 1 and minus 1 becomes 0. So this is 0 if yi is not 0 for any I. And it's not 0. And what is it when it's not 0? When it's all 0, when everything is 0, then what happens? You're multiplying 2 n times. So it's a 2 to the power of n if yi is 0 for all I. So there are different things here. So now let's conclude here. So we still have an assumption that f is constant. That's why we have this. Originally, we have f of x. Okay, we cannot get rid of this. Now, what happens here? Everything vanishes. Every coefficient becomes 0, except when all the digits of y becomes 0, which means y equals to 0. So even though there are 2 to the n minus, it seems like there are 2 to the n terms in this big summand, everything is just vanishing except when y equals to 0, except the zero cat state. And the coefficient of that zero cat state is 2 to the n. Okay? So we have canceling out 2 to the n. So the final state in the constant case, if the function was constant, the input register all goes back to 0 cat. Okay? So what does that mean? If it's constant, you will always get 0 in the measurements of every n input register. So remember, this measurement at the end is you're taking a measurement on n qubits, every n qubit. You cannot miss any of them. So because you need to make sure that every qubits in the input register reads as 0 to find that this is actually 0. So now what's the catch? So I don't have time, but I will just conclude and write it here, and then we'll resume next time. If f is balanced, then psi 3 has no quantum state no quantum state, zero cat. No. How do I write this properly? Has no cat zero in its state. In it, or just okay, just come in it. So which means that now look at again here, this one again. So y is from 0 to 2 to the n minus 1, right? Normally you want to see that there are 2 to the n different terms. But it turns out that if f of x is a balanced function, then the coefficient of 0 cat vanishes. So what does that mean? When you take a measurement on the input register, you will not gonna have the situation where you measure 0 every single input register. At least one of input register must be read as 1, right? So this means if you observe 1 on at least one input register, then f is balanced. So that's the Judge's algorithm. All right, so if you have any question, let me know. We'll see you on Monday.